Quant explained, breaking down quant finance concepts. Introducing quantum computing. Introductory concepts. What is your name and what do you do?
Hello, I'm Tomasz Ćwik, co-founder and CEO of finQbit, a startup which merges deep tech and fintech together to solve complex problems in risk management.
What is quantum computing and how does it differ from classical computing?
I would say that quantum computing represents a fundamentally different approach to computation compared to classical computing, which is what we know from our laptops and devices. And classical computing is based on a very clear and understandable model. Data is processed in binary, meaning that every bit can be either 0 or 1. And this binary system underpins everything from our mobile devices to even massive supercomputers. And in classical computing, each operation is performed sequentially. And although modern processors can perform operations incredibly fast and even handle multiple tasks at once through parallel processing, it's still kind of hacking the nature and trying to bypass the nature, as they are not paralleled by default. And quantum computing, however, does not operate within those binary constraints. Instead of bits, quantum computing uses qubits, which fundamentally behave differently from classical bits. While the specifics of qubit behavior involve complex physics, the key takeaway is that qubits enable quantum computer to process a vast number of possibilities simultaneously. And this isn't because quantum computers are simply a faster version of classical computers, but rather they operate using a completely different set of rules which govern how information is processed. And this leads to a major practical difference: problem-solving approach. And classical computers tackle problems by running through each possible solution until the best one is found, which is effective but can be time-consuming for very complex problems. And quantum computers, by contrast, can analyze multiple possible outcomes at the same time. And this ability makes them exponentially good at solving certain types of problem that are too complex or time-consuming for classical computers. For instance, in a field like cryptography, drug discovery, or complex system modeling like weather forecasting or financial modeling, quantum computing offers the potential to process information and reach conclusions much more effectively than classical computing. Another major difference lies in scalability. As problems became more complex, classical computers require a linear increase in resources to handle that problems, and meaning that we need proportionally more processing power and memory. Quantum computers, however, theorize to scale exponentially with additional qubits, and this means that with every next qubit, we are able to double the power of quantum computers, which is one of the main advantages over the classical computer. However, it's important to note that quantum computing is not simply replacement for classical computing. It's rather a supplementary technology. For many everyday tasks, classical computing is more than sufficient and more practical, and quantum computing is currently suited to specific types of problems and calculations where it can leverage its in unique capabilities. So, in summary, I would say that while both types of computing aim to solve problems, the way they process information and the type of problems they are suited to solve, they are fundamentally different.
What are the key principles of quantum mechanics that are leveraged in quantum computing?
Quantum computing leverages several fundamental principles of quantum mechanics to perform computations in a way that classical computers cannot. And these principles include superposition, entanglement, and quantum interference, each playing a crucial role in enhancing the capabilities of quantum processors. However, I would say, as one of the father of quantum cryptography, Arthur Eckert, that it's all about quantum interference, which plays a pivotal role in functionality of quantum computers. It's all about harnessing and managing the way wave function combine, representing the probabilities of qubit states. In quantum computing, every computation essentially involves navigating paths through a landscape of probabilities. So, quantum interference enables the constructive addition of wave function associated with correct answers, while destructive cancelling out of associated with the incorrect answers. So, this process is crucial because it directly influences the likelihood of quantum computers arriving with correct solution. And quantum algorithms are designed to amplify the paths leading to correct solutions via constructive interference and diminish the paths leading to incorrect solutions through destructive interference. So this selective amplification is what makes quantum algorithms exceptionally powerful for certain computational tasks, such as factoring large number much more effectively than classical computers. And by manipulating the phase of those probabilities, quantum computer can effectively tune the interference patterns that emerge from the computation. So essentially, that the system evolves towards the correct answer. And the strategic use of quantum interference is thus not merely a feature of quantum computing, but the backbone of its operational promise, enabling quantum computer to explore and exploit a computational landscape far beyond the reach of classical computers. So this makes quantum interference a cornerstone of quantum computational power, driving advancements in cryptography and optimization, simulation tasks across various scientific fields.
Can you explain the concept of qubits and superposition in quantum computing?
Understanding qubits and the principle of superposition is, I would say, essential to grasping how quantum computers operate and why they offer such promising advances over traditional computing model. And classical computer bit is the most basic unit of data in computing, which can be in two states, 0 or 1, which we mentioned before. And every piece of data and every operation in classical computing can ultimately be broken down to these binary states. However, quantum computing uses qubits, which differ significantly because they can exist in multiple states at once thanks to quantum phenomena known as superposition. And superposition is a counterintuitive principle where quantum systems such as qubit can be in multiple states simultaneously. Uh, it's very often to use the parallel of light switch that usually we can have light switch on or off. In quantum world, we can be in both. So the light is on and off in parallel. But more clear case is with the spinning coin, where we have heads and tails. So that when the coin is spinning, we have both states in parallel until it will collapse. Then we know which state we have. So it captures the essence of superposition. So in practical terms, qubit can be 0, 1, or any quantum superposition of this state. So this it is represented mathematically by a vector in two-dimensional complex vector space, where the coefficients of the vector describe the probability amplitudes of the qubit being in the basic state 0 or 1. So the power of superposition allows quantum computers to perform many calculations at once. So for instance, whereas a classical computer with 3 bits can represent any of the 8 possible combinations of these bits at one time. So we can have 0, 0, 0 or 0, 0, 1 till 1, 1, 1. A quantum computer with 3 qubits can represent all 8 combinations simultaneously. So this ability to handle multiple states at once exponentially increases with more qubits. So with each additional qubit, the computational power of quantum computer grows exponentially rather than linearly. So this leads to a massive parallelism in computation, which is not achievable by classical computers. So, moreover, the implementation of algorithms designed to exploit superposition can lead to significant reduction in the time complexity of various computational tasks. So, this includes famous quantum algorithm like Shor algorithm for factoring large numbers, or which underpins, by the way, the modern cryptography, or for instance, Groover algorithm.
What is quantum entanglement, and why is it important for quantum computing?
Quantum entanglement is another cornerstone of quantum computing, described by Einstein as spooky action at a distance. So, in practice, entanglement allows 2 or more qubits to become so intrinsically linked that the state of one instantaneously sets the state of the another, regardless of the distance between them. So, to put it simply, let's visualize 2 coins, each with a head or tail side. So picture someone placing one coin with heads up in one box and the other with tails up in a second box. The location of each coin is unknown to us. And now imagine the scenario that, for instance, Alice receives one box and travels to San Francisco, and while Bob takes the another and goes to Tokyo. Neither knows which coin they possess. And however, the moment Alice opens her box and sees the heads, she immediately knows that the tails are in the Bob box, so regardless of the distance between them. However, it's not completely true how it works. My university friends would kill me for such oversimplification of quantum entanglement. So let's use our imagination and modify this example. Unlike our example where the coin state is predetermined because somebody put them to the box, true entanglement suggests that each coin outcome is undecided until one of the boxes is opened. So at this moment, the state of the coin becomes fixed. So importantly, entanglement implies a dependency between the 2 coins. If Alice finds heads, Bob will find tails. So this linkage is crucial for quantum computing because it enables a level of synchronization and correlation between qubits that can leverage to perform complex calculations much more effectively than classical computers. And entanglement is employed in various quantum algorithms and is particularly important in error correction and quantum teleportation. Quantum error correction, which is crucial for the practical use of quantum computers, relies on entangled qubits to stabilize the quantum state against the decoherence that naturally occurs in our high entropy world. So, meanwhile, quantum teleportation, which involves transferring quantum information between qubits at different locations, uses entanglement to achieve what is effectively and instantaneously transfer of state information, crucial for creating quantum networks and long-term quantum communication. So the profound implication of quantum entanglement is still being something explored, as it surprised even Albert Einstein.
For more on quant finance, join the CQF Institute now.